Swayam Prabha. Digital India. Educated India.
In this lecture, we'll be designing PID controller for our plant to be controlled. We'll validate the concept we discussed in the earlier lecture, the Ziegler-Nichols rules and root locus. So we'll be using those methods to come up with the PID controller. And we validate this approach through the example. So we have example. Consider the transfer function of PID controller and plant as GC of S, the controller transfer function, which is KP plus KIS plus KDS, and GP, which is the transfer function of the plant, 4.0 divided by S into S plus 1, S plus 2. So here KP, KI, and KD are the PID controller gains. In the plant only has the poles at S equal to 0, S equal to -1, and S equal to -2. There is no 0 in the system, only they have poles. And if you look in closed loop control system and how this controller transfer function and plant transfer function are arranged, let's look. The closed loop control system we have reference signal to be tracked or to be regulated. This is my PID controller GC of S, which is KP plus KI by S plus KDS. And the output of the controller goes to the plant. The plant transfer function denoted by GP of S, which is 4.0 divided by S into S plus 1, S plus 2. This is the controller, plant transfer function output, which is we can denote by OIS, and this is the feedback, negative feedback, minus plus. This is the problem we are given, and we have to design the PID controller. So the problem can be formulated as design a PID controller for the above system using Ziegler-Nichols rule. You find the overall closed loop transfer function and find closed loop system poles comment on stability of the control system based on pole locations. So this is basically autopilot design if you look. So this is closed loop control system. We are designing PID controller here to control the system. Let's move the solution part. So here, let's consider the only control variable to be varied, Kp, the way we have done before. So here, only control parameter for the root locus will be considered Kp, which is varies from 0 to infinity. And we assume Kd equal to Ki is 0. The open loop transfer function, which is G naught S, Gc of S, Gp of S, H of S. So H of S is 1, which unity feedback we are assuming. So Gc for this condition, GCL to be only Kp, and Gp is 4.0, S into S plus 1 and S plus 2. And the characteristic equation of the system 1 plus G naught S equal to 0. We can write 1 plus 4 Kp S into S plus 1 S plus 2 equal to 0. Now for G naught S, the number of zeros, which is basically M. So here, if you notice, in the open loop transfer function, we have no zeros, so M equal to 0, and number of poles, which is denoted by N, equal to 3. The poles are given by S equal to 0, S equal to -1, and S equal to -2. And the location of the poles in the S plane, we can write here we have S equal to 0, here S equal to -1, and S equal to -2. The real part of S, imaginary part of S. So now we first find the breakaway point. For finding the breakaway point, we have to consider the characteristic equation. Now, finding the breakaway point from characteristic equation. So we have characteristic equation 1 plus 4 Kp S into S plus 1 S plus 2 equal to 0. And so we have to find the gain from this expression. So Kp is the only gain here, minus S plus 1, S plus 2 divided by 4. Now we have to take the derivative of Kp with respect to S. So dKp ds minus S plus 1 S plus 2 divided by 4 minus s into s plus 2 divided by 4 minus s into s plus 1 divided by 4, which is nothing but equal to 0. And from this expression we can write s plus 1, s plus 2 plus s into s plus 2 plus s into s plus 1 equal to 0. From this expression we can write s squared plus 3s plus 2 s squared plus 2s plus s squared plus s equal to 0. And if we simplify, it yields to be 3s squared plus 6s plus 2 equal to 0. If we solve this quadratic expression, we are having the values of s as s equal to, we can write minus 6 plus minus 36 minus 24 divided by 6. We simplify further, minus 6 plus minus 12 divided by 6, 3 plus minus root 3 divided by 3. So here, if we denote, since there are two roots, we can denote s1 and 2, which comes out to be minus 1.577 and minus 0.422. Here, if you notice, here s equal to minus 1.577 does not lie on the root locus. Hence, this is very clear because the center of CG of asymptotes will have one. I'll show this after some time. So why it is not the desirable point for the root locus to be breakaway, and hence the breakaway point exists at s equal to minus 0.4226. Now let's find the angle of asymptotes. Let's find the angle of asymptote. So here number of angle will be n minus m, which is 3. So there will be 3 angles. So let's find those angles. Phi equal to 2 cube plus 1 divided by 3 into 180 degree, and where key equal to 0, 1, 2. So for q equal to 0, phi 1 yields to be 180 degree divided by 3, which is 60 degree. For q equal to 1, phi 2, 3 by 3, which is 180 degree. And for q equal to 2, phi 3, which is 5 into 180 degree divided by 3, which is 300 degree, which is nothing but minus 60 degree. And the centroid of asymptotes, the centroid of asymptotes, we can find summation of real value of pole minus summation of real value of zeros divided by n minus m. So which is minus 0 minus 1 minus 2 divided by 3 but there is no zeros, so only poles are there. So minus 3 divided by 3, which is minus 1. So now I'll connect why we have taken the breaker point. This is our breaker point. So here centered is minus 1. That's why we can't take this value for the breakaway point. Now it is clear, I hope, why you have taken is equal to minus 0.4226 for the breakaway point. Now we'll find the point where the root locus crosses the imaginary axis. So now let's find the point where the root locus crosses the imaginary axis. So for this, we can come up with the characteristic equation, and we can use the method of Routh stability criteria, and we can find that value. The characteristic equation already have the characteristic equation, because to apply the Routh stability criteria, we have to come up with the expression of the characteristic equation of the terms of the system. Characteristic equation of the closed loop transfer function is given by s into s plus 1, s plus 2 plus 4 kp equal to 0. And if you simplify, s cube plus 3s squared plus 2s plus 4 kp equal to 0. Routh array, the way we have done during the study of Routh stability criteria. So the highest power is 3. So S3, the row will start from S3, S2, S1, S0. And for S3, we can form the row 1, 2, 0. And for S2, 3, 4 kp. For S1, we have to multiply 3 into 2, 6, minus 4 kp divided by 3. And the remaining part will be 0. And this expression is not 4 kp. So this Routh array, from this array, we'll find the value of kp at which the root locus crosses the imaginary axis. And now, using sufficient condition for stability, as you have done, all the terms in the first column should be positive. For that, we need to, and this expression should be greater than 0. We get 6 minus 4 kp divided by 3 should be greater than 0. From this, we can find the value of kp should be less than 3 by 2. Hence, we can write, hence, the limiting value of kp for stability is kp equal to 3 by 2. Why? Because for this value, the expression or the row for S1 will be 0. So this is the limited value. So if AP is greater than 3 by 2, then the system becomes unstable, since root locus moves to right hand side. Now using in the characteristic equation yields Kp equal to, we can write 3 by 2 here. We write here. In the characteristic equation, we have the characteristic equation SQ plus 3s squared plus 2s plus 4 into 3 by 2 equal to 0. And after simplifying, s cube plus 3s squared plus 2s plus 6 equal to 0. And the roots of this expression, roots are s equal to -3 and there are two complex conjugate roots, 1.41 or 21j. Hence, so this is the values at which, this is the values of s at which Kp equal to 3 by 2. Since we are interested the values of s at which the root locus crosses the imaginary axis. So s equal to plus minus 1.41421j. Now also we can find the ultimate gain Kp from the magnitude condition as following. Now using the magnitude condition, this part already we have done the last lecture, the magnitude condition. So G naught is the magnitude of the open loop transfer function should be equal to 1, and from this we can write 4Kp divided by s into s plus 1, s plus 2 equal to 1, and add value substituting s equal to plus 1.41421j comes up to be, or we can say plus omega j, because this is the frequency omega. So here omega equal to, we can write 1.41421. Substitute these values. Let's write this equation number 1. In equation number 1, we can write ultimate gain KPU, we can write S into S plus 1, S plus 2 divided by 4 at S equal to, we can write 1.41 421. We can, if we substitute this value, the value yields to be 1.41421 divided this to the I. Let's say we can write it is 4 into 1 plus 1.41421 squared into 4 plus 1.41421 square, and after simplifying, the value is 1.5. So the KP, the ultimate gain from the above analysis, we can write KPU, or we can write the ultimate gain, the ultimate gain for KP, it's KPU, which is 1.5. Now, if you draw the root locus for this particular system, we have the imaginary axis, real axis, this is IMS, RES, and we are having the centroid of asymptote is -1, and which is basically, so there are two root locus at is equal to 0, this is equal to -1, and is equal to -2. So we have the asymptote angles. One is 60 degree, and so here is equal to -1 is the pole, but also the CG of the asymptote also -1, and we have another root locus is here, which is starting from s equal to -2 and goes to 0 infinity, and we have breakaway point somewhere which is minus, which is minus 0.4226. This is our breakaway point, and root locus goes like this, and this is the point we are having. At this point, KPU is 1.5, and the omega equal to 1.414. So this is these two values are required for finding the PID gains of the PID controller. So now we'll design the PID controller. So for that, we have to find the time period. What you have done in the previous lecture, TU, we can find 2 pi by omega, which is 2 pi by 1.41421, which is 4.4429, and using Ziegler-Nichols rule, the PID gains are Kp equal to 0.6 into Kpu, which is 0.6 into 1.5, which is 0.9, and Ki 0.6 KPU. This is the expression for Ki and Tu, and which is the value comes out to be 0.4051. KD equal to 0.6 KPU into 0.125 TU, and if you substitute the values of KPU and TU, the value yields should be 0.4998. The PID controller, now we can design the PID controller. You can write the expression of PID controller GC of S equal to 0.9 plus 0.4998 into S plus 0.405 divided by S, or we can write 0.498, this value we write 0.498 S square plus 0.9 S plus 0.405 divided by S. So this is our PID controller, and the closed loop transfer function we can write the closed loop transfer function as we asked in the problem, Ys divided by Rs equal to Gc of S, Gp of S 1 plus GPS, GCS, and if you substitute the values for GC of S 0.498 S square plus 0.9 S plus 0.405 divided by S into 4 by S into S plus 1, S plus 2 divided by 1 plus 4 into 0.498 S squared plus 0.9 S plus 0.405 divided by S squared into S plus 1, S plus 2. So this is the closed loop transfer function, and if you further simplify, we have the expression 4 into 0.498 S squared plus 0.9 S plus 0.405, this is S, divided by S squared S plus 1 S plus 2 plus 4 into 498 S squared plus 0.9 S plus 0.405. So now you can find the poles of this characteristic equation. From the denominator part, you can find the number of poles. So here the characteristic equation of this closed loop transfer function we can write S squared into S plus 1 S plus 2 plus 4 into 0.498 S squared plus 0.9 S plus 0.405 equal to 0. So if you solving this equation, we can get the poles. of the characteristic of the closed loop control system. So this is the task for you. You can find what are the poles coming out to be from this characteristic equation, and you can comment on stability. So let's stop it here. We'll continue from the next lecture. Thank you.